Today we shall be looking into some estimation methods of some more thermophysical properties of natural gas. In the last lecture we learnt about the gas specific gravity, and now we shall look into some more. In this case we are going to look into these properties like compressibility factor, then viscosity, density, compressibility. First, let us come to the compressibility factor. What is this? We know that by definition, whenever we have some real gases, they behave differently from an ideal gas. For a given temperature pressure, we know that an ideal gas will be occupying certain volume, but the real gases will be occupying some other volume. This is not only true for the volumes, but it also is true for many other properties which at the same temperature pressure for the same component for ideal behavior and non-ideal behavior. So, this compressibility factor is specifically regarding the volume changes. So, this is defined as a ratio of the actual volume occupied by a gas at certain temperature and pressure to the volume occupied by the same gas at the same temperature pressure, provided that it were behaving ideally. So, taking it to the in terms of the PVT, that is pressure volume temperature relationship, we find that it can be easily found out that PV by nRT. In this case, nRT by P is the ideal volume, whereas V is the actual volume. P is pressure, T is absolute temperature, and R is the universal gas constant. Perhaps all of you know the difference between the universal gas constant and the gas constant. The gas constant is a function of the type of gas. However, the universal gas constant is a constant which is applicable for all types of gases, and N is the number of moles. Now, if I know the value of the Z, I can know the deviation of the gas behavior from ideality. Now, if we look at this definition, we find that if both the volumes become the same, it means Z will be equal to 1. That means if Z is equal to 1, this signifies that the gas is behaving like an ideal gas. So, any deviation from the Z, whether it is on the higher side, that is more than 1, or on the lower side, that is less than 1, will tell us that the gas is not behaving ideally. So, that is why this Z is also sometimes called gas deviation factor. Generally, it has been found that the volume of the real gas is less than the ideal gas. So, less means as if it is occupying less space. So, less space means as if we are compressing it extra, it is under a more compression. So, that is why it is having less space. So, if it is having less space, it is called as if super compressible. Real gas is sometimes called super compressible, and hence this Z is also sometimes called the super compressibility factor. But more common is the compressibility factor. Here in this figure, I have shown some typical values of the Z for some few gases, and how with respect to the pressure. Here you see that the value of the Z is changing. So, for example, let us take methane. Methane is the primary component of the natural gas, and we see that initially as we increase the pressure, it is deviating from 1. It is starting with one unity, that is it is ideal gas, and as I increase the pressure, I find it is deviating, it is coming down, and then again it is rising, it is crossing the Z equal to 1, and again for further increase in the pressure it becomes more than 1. That means only for at some point it is ideal behavior is maintained, and rest of the part it is behaving like a non-ideal gas. Similarly, another important component is nitrogen. We find its behavior is different. It is the value of Z in case of nitrogen, it never comes down below 1. It almost remains 1 for some time, for still some higher pressure, and then slowly and slowly it goes above the value of 1. If you look at hydrogen, we find that it is starting with 1 and its value quickly rises to a value which is more than 1, unlike the nitrogen. Then we have ammonia. For ammonia, we find that value goes much below unity, and then after a increase in the pressure, it starts slowly rising, and at some very high pressure, it goes above 1. So these particular figure shows that at a given temperature 25 degrees centigrade, how the various gases are behaving with change in the or increase in the pressure. So we find that a gas would behave ideally at higher temperature and lower pressure. So as we increase the pressure at a given temperature, it will go towards non-ideality. Similarly, if we reduce the temperature at a given pressure, again it will go towards non-ideality. Here we have several types of methods which are used to estimate the compressibility factor. They may be given in terms of some diagrams, and these diagrams are generally represented in terms of reduced pressure and reduced temperature for single components or pure components, whereas with respect to pseudo reduced pressure and pseudo reduced temperature for gas mixtures like natural gas. We may have some empirical correlations based on some experimental data, and these correlations generally contain many coefficient values and are applicable for certain range of pressure, temperature and composition. And lastly, we have many equations of state, and some of them are like we perhaps know van der Waals of equation state, which was proposed the first time to account for non-ideality. Later on, many other non-ideal or real gas equation of state were proposed, and some of them have been given here like Peng Robinson, Swab, Redlich Kwong, Benedict Webb Rubin. There are just a few. There are several equation of state reported in the literature, which you can easily find out from a standard thermodynamics book. Here we come to a typical representation through a diagram of the compressibility factor in terms of the reduced pressure, which is given on the x-axis, and reduced temperatures, which are there for various types of curves shown here, and on the y-axis we have the compressibility factor. Now, for example, you can see that this set of curves are applicable from about 1.05 to 3 reduced temperature. That means the reduced temperature is 3 and 1.05, this is the range. When I am saying reduced temperature pressure, please understand this may also applicable for whether it is single component or whether it is a mixture. So I will not be always saying pseudo reduced. When reduced means either single component or pseudo reduced. And here we find the set of curves which are again applicable for gives a more what do you call resolution in terms of this TR. Here it is 1.05, 1.5, etc. Here we find 1.05, 1.1, 1.15, etc. Okay, so this gives you more resolution for the values of the TR. Now here we show a typical expression. This is an expression from this experimental data. It's empirical correlation, which you can see the complexity of the equation. It is so very complex. So here we find that it is given in terms of the pseudo reduced temperature, pseudo reduced pressure, and the logarithm, and there are so many coefficients involved in these equations. All these are coefficients involved, and this particular equation has been obtained by considering the experimental data. And this is a very recent publication. Here is the publication from which this correlation has been taken. And if you look into the books on referred books which I have put at the end of the lecture, you will find different types of correlations have been given in those books. This is the one I am showing here is one which is very recent one. Next we come to another important property, that is the gas viscosity. When we say gas viscosity, we mean the dynamic viscosity or absolute viscosity. Perhaps you know there is another viscosity which we call the kinematic or kinematic viscosity, that is the ratio of the dynamic viscosity to the density, that is the kinetic viscosity. So when I say viscosity, it means dynamic viscosity, and viscosity is what? It is a measure of the resistance to the flow of a fluid over a surface. The surface may be a closed surface like pipeline, or it may be an open channel like in a river. So here the viscosity is having this dimension of viscosity is that mass per unit length per unit time, and in SI unit its unit is Pascal second. But a very more common unit of viscosity is poise or centipoise. 1 poise is equal to 1 gram per centimeter per second, and centipoise is 10 to the power minus 2 poise. The poise comes from the name of the famous scientist Poiseuille. Perhaps you know in fluid mechanics we learn about Poiseuille flow, Hagen-Poiseuille flow in a tube. Okay, so from the name Poiseuille we have reduced it to poise. Now this, by knowing the viscosity, we can estimate the pumping power, because the more the resistance, the more will be the pumping power. And in case of natural gas and oil, that it predicts that how much oil, gas or water would be produced when we are drilling any reservoir, because how much gas or the oil will be coming out through the pipeline will be determined by the viscosity. And again, this value can be obtained, or it has been reported in various manners like tabulated data for several types of compositions at different temperatures, pressures. Then we have graphical form or semi-empirical relations, and from some nomographs. Here I have shown a typical viscosity representation through a diagram of a few components. Like here on the x-axis we have temperature, and on the y-axis we have the viscosity, and this viscosity is in terms of 10 to the power minus 6 Pascal second, and the pressure is 1 atmosphere, that is at lower pressure. And here we have shown several components starting from methane, ethane, ethylene, propane, so on and so forth. Here we have hydrogen sulfide, here we have carbon dioxide, nitrogen, air, helium, and on this side we have the higher hydrocarbons. What we find here, that at a given pressure, as we increase the temperature, the viscosity increases. Okay, and also what we find, for a given temperature, as the molecule becomes heavier and heavier, the viscosity is decreasing. So, okay, so helium is having a very high viscosity effect, whereas this decane or something is having a low viscosity effect. And next we represent the viscosity in terms of the reduced temperature and reduced pressure, and this is more handy because here we do not need to bother about the component. Here we have the viscosity ratio. This is applicable to estimate the viscosity at a higher pressure. The first one, if I know the viscosity at lower pressure, then by knowing the viscosity ratio, which is defined as the viscosity at the atmospheric pressure to the viscosity at the reduced pressure and reduced temperature. So, if I know from the previous graph, we know the viscosity at 1 atmosphere, and this value along with the value of the viscosity ratio, we can find out the viscosity at any given pressure temperature. So, here on this x-axis we have the reduced temperature, and on the parameter wise the different curves are representing the different reduced pressures. Here we have shown another curve this is a very peculiar about the hydrocarbons, especially natural gas and oil. In this case, we find there are three sub curves here, which are accounting for the presence of H2S. This is nitrogen and this is for carbon dioxide. That means once from the previous curves we know the viscosity of the natural gas, then we should use this curve to give a correction due to the presence of the H2S, N2 and CO2. Coming to another representation of viscosity, we have several correlations in the literature. The various books on the natural gas will be giving you various types of correlations, and whatever the correlations may be, there are some common points among the correlations, and these are that all the correlations have composition of the natural gas in them, and they account for the presence of both the hydrocarbons and the non-hydrocarbon components in the natural gas, and naturally all the correlations must be giving us or taking into account the pressure and temperature variations for different ranges. So with this, I have put here one correlation that has been published recently. This correlation has been proposed for both the sour natural gas and sweet natural gas. When I say sour natural gas, it means the natural gas that contains the acid gases like carbon dioxide and H2S, whereas sweet natural gas is the one which does not contain these acid gases. So these authors gave this particular correlation for the sour natural gas, and here we find again there are coefficients A, B, C, D, E and F, and these have been listed in this particular table. And this is for the sweet gases. Again we have A, B, C, D, E, F. Now you can see there is a difference in the type of the correlation and there the coefficient values. And here we have the listed this have listed, and these correlations have been given in terms of the pseudo-reduced pressure and pseudo-reduced temperature. Next we come to gas density, and generally gas density is estimated from a suitable equation of state. We know that for an ideal gas, the gas density is given by this expression Pm by RT, pressure into molecular weight divided by the universal gas constant and the absolute temperature. Whereas for real gases, we include the value of Z, about which we have talked earlier. Now with this knowledge, we go to the last property in this lecture, that is the gas compressibility. Please mind it, this is not same as the compressibility factor. This compressibility factor is talking about the deviation from the ideal behavior, whereas the gas compressibility indicates that how the density or the specific volume of the gas would change with pressure at a given temperature. Okay, the rate of change, how the density would change with pressure at a given temperature is given by the gas compressibility. So it is given by a notation called Cg, C for compressibility and G for gas, and it is defined like this. It is minus 1 by V dou V by dou P at a constant temperature, and this V is the specific volume, which is nothing but the reciprocal of the density. Now why the negative sign has been given? So that to account for the fact that with the increase in the pressure, the volume reduces at a given temperature, that we know from Boyle's law. So dou V by dou P will always be negative, and that negative and this negative will keep the value of the Cg positive. So that is why this negative sign has been put, but contrast it with in terms of the density. Now because density is reciprocal of the specific volume, so density will increase with increase in pressure at a given temperature. So there is no need of putting any negative sign. So we find that in this expression there is no negative sign. So this is the way we can get the value of the gas compressibility, and to further estimate this value, we simply need to know the equation of state. That equation of state will give us an expression for the V as a function of temperature pressure. So, if I know that, we differentiate that with the pressure, keeping the temperature constant, and we use this expression to get the value of the compressibility, gas compressibility. We will do here I have now shown that for a real gas, how we can rearrange that expression, okay, that Z equal to PV by nRT. From that, how we can differentiate that expression, and we can get this particular, this you can also derive. Here I have shown that how the gas compressibility is getting from the real gas equation of state. Here we have represented this in terms of the pseudo critical pressure and pseudo reduced pressure at a given temperature. This is because that we have earlier seen that how we can obtain these values from the diagrams also. Here you see, as we are talking about reduced values, similarly we can also talk in terms of the reduced compressibility, that is given by CR, and CR is given as CR equal to Cg into the pseudo critical pressure. So, this is the way we can get the value of the reduced gas compressibility. So, this is the definition. So, we have to accept it at its face value. And here we show the chart for the CR into TR, and here from this basically the charts are nothing but showing the reduced compressibility, from which we can find out the actual compressibility. And here we are seeing that this is containing this from this is the x-axis is representing reduced pressure, whereas the y-axis, these various curves are made for the reduced temperature. The difference is this, that here the range is smaller, and in this thing the range is larger. It is going from 1.05 to 1.40, whereas in this case it is going from 1.40 to 3. So, these two curves together may be used to find out the gas compressibility from the knowledge of the reduced gas compressibility. And these are again a few references which you may consult to understand these properties further. Thank you.